All right, so what we do today, we talk about...
I have a question, kind of annoying, but do you think we're gonna get both? Oh, wait, I don't know.
Say it again, Marcel. It was choppy. I could not understand.
Yeah. I think my internet's unstable, but I just wanted to ask, I know it's an annoying question, but do you think that we're going to end up having a third exam and the final?
Yeah, sure. Don't worry.
There'll be enough time?
For whom? For you or for me?
For my sanity? I don't know.
Well, you know, I'm hoping, first of all, I'm glad that you're working on the exam, you know, truly that you're considering this material. I think we will have quite a lot of leeway. Originally, the final exam was supposed to be an in-class exam, right? In other words, the grades usually they are very skewed towards the hundreds when people do a take-home exam, and so the final exam was a way to chop the rye, to make it shorter. So I don't think I will do that now. So it will be just a take-home exam, most likely one that would have been intended for people to take in class within 2 hours. So there should be enough time. But you let me, we'll see what happens. You let me know how you feel about second exam as you work through it. And again, I will do my best to help you. Okay. So anyhow, so let's get to the material. And don't be too worried about it. Just worry about trying to understand this material and enjoying it. So Bertrand's paradox. We have a chord, and the chord is randomly drawn on the circle, and the circle is of radius r. What's the probability that the chord is shorter than the length of a side of an inscribed triangle? So first of all, there is geometry involved in this question. Later on, I'll present Buffon's problem. Well, the geometry is going to be slightly more complex. So let's try to understand first of all, what is an inscribed equilateral triangle? So you might come to a realization that I can produce an inscribed equilateral triangle by drawing 3 radii here in blue, and then spreading them evenly, right? Equilateral triangle means that each of the 3 sides has the same length. So that can be produced by spreading the radii evenly. Make sense? And if they are spread evenly, that means that the angle between them, well, total angle is 2 pi, and the angle between any 2 has to be therefore 2 pi divided by 3. So this then produces and then this produces the skeleton for the equilateral triangle. It's then easy to figure out the length of the chord. The length of the chord is simply, you can use trigonometry. This is radius r. This angle is 2 pi over 3. If I cut it in half, then I have the angle is pi over 3. Half of it is pi over 3. And the chord here is just sine multiplied by r, sine of pi over 3 by r. That would be the length of this chord, correct? And then I just have to multiply it by 2 for the full length. For the full length, I have to multiply it by 2. So I know what's the length of the chord. And now there are 2 ways to understand what randomly means here, right? So one way to imagine that the chord is drawn randomly is that it's like a stick of infinite length that can fall on the circle. It can fall basically anywhere, but it will intersect the circle, right? It could fall here, here, here. It can fall anywhere. Now you can make a simplifying assumption as follows. So imagine that that the circle is below a glass, and you can rotate it. Okay, so what happens is that you drop the chord on the glass, and then rotate the circle in position so that the chord can be assumed to be parallel to one side that you designated, this side, for example, right? So where the angle 2 pi over 3 is drawn. Make sense? So there is a glass table, and below the glass table, a rotating platform. The lecture is being recorded. So you have a rotating platform, okay? And when I drop the chord, I rotate the platform so that this side is this designated side of the inscribed triangle is parallel. Yes, and then what happens then is that the chord is equally likely to fall anywhere on the y-axis from this point, a distance r, all the way to this point, a distance 0. Right. So the r then the point on r is then equally distributed. That's one interpretation of randomness. Correct. So I will do this. Right. So I will let one distribution be the distribution of r. So where the chord falls is anywhere between r equals 0, that's here, so between y equals 0 to y equals to r, uniformly. Good? Which means that, so can you tell me then what is the density function for this uniform random variable, please? So you understand, guys, what I am asking, right? So yes, I am asking. So first of all, did you understand the setup? So this question, I try to understand what it means to randomly draw a chord. So what I personally imagine is that I take a very, very long and thin metal stick, and I drop it on a glass table. Okay, I drop it on a glass table, and the glass table has a circle inside underneath it. Okay, and the circle I rotate into position. Okay, because by symmetry, right? It falls somewhere on the table, and then when it, you see, now we have interference. In other words, black cat interference. Anyhow, it was about to chew the wire. So where was I? So we have this circle. Once I drop, right, the chord intersects somewhere on the circle. Could be not like I showed in the picture, right? Not on the XY axis, right? But I can then rotate the circle underneath so that this designated side of the chord is parallel. Make sense? So in other words, I can imagine that the chord is always dropped perpendicular to the y-axis. God damn it. You see? Yes, usually he's sleeping at this time, but I guess he decided he's up. He wants something. So yes, okay. We have this this red line is then perpendicular to the y-axis always. Yes, and now if it's dropped, you might imagine that randomness means that y is anywhere between 0 to r. So in other words, this point here, where the chord intersects the y-axis, is randomly distributed between 0 and r. Yes. So my setup, does it make sense so far, guys? Yes. So then my question was, what's the density function? So Elias said this between y is between sine of 0 and sine of pi. Well, I mean, you can just don't use trigonometry first of all, right? I think you can say between 0 and -1. That's fine. But better just we have this already axis, and for whichever reason we decided to set up this to have radius equal to r. Yes, it's obviously not important. You could have readjusted, renormalized r to be equal to 1, and that will not affect probability, right? You can always assume the circle is of radius 1, but just for the setup as I drew it, let's say simply in terms of R. So then the distribution Y is between 0 and R. Yes, but what you said, Eli, is perfectly, it's the same, it's symmetric, right? And then I need to find the density function. If it's uniform, what's the density function? So so Shulamit is asking why don't we care? Let's say maybe it's below this this x-axis. So this is the point here, right? So when the chord actually is dropped, if you are looking at a stationary table, the chord can be dropped like this or like that, right? It can be dropped in so many ways, correct? So the chord can be dropped like this, the chord can be dropped like that. It doesn't have to be a parallel line, and it doesn't have to be above the x-axis. But basically, you can use symmetry, right? The circle is symmetric. You can then readjust this idea that you can readjust it by imagining that the chord falls on a glass table, and the circle below it can then be rotated into position, right? Because the length of the chord is, it's not affected, right? This is going to be the length of the chord from this point to that point. If I rotate the circle below it, it's not going to affect the probability. So I can always rotate the circle into position so that this is the picture I see. I rotate it below. I first drop the chord and then I rotate. So then I can imagine that what's happening is essentially the chord is equally likely to be distributed from 0 to R. Yeah, I reduce the whole situation. So if I basically I rotate when the chord is dropped, I rotate until this piece is parallel to the chord, and then that's the picture I can always see. So that now I reduced it to the idea that the chord, when it's dropped uniformly between 0 to R. Okay, and then I need the density function for it. What's the density function if it's uniform between 0 and R? Uniform random variable is the simulation of every event being equally likely, right? Every place being equally likely. And so that means that the histogram generated would be a rectangle, correct? Equally likely means that if I were to simulate it, the chord will be dropped in every region. If I divide this axis into very small regions, exactly, Josh. It's 1 over R, that would be, because the area must equal to 1. And when you draw the histograms, if it's dropped randomly, then I can imagine dividing the upper y-axis between 0 and R into many tiny segments, and then seeing if I simulate how many times does the chord drop in those regions. And if it's random, then it's equally likely to drop between any of those regions. So the histograms have the same elevation. So that generates a rectangle. Make sense? So when you think of continuous random variables, I find it helpful to think of discrete random variables with just very many dense outcomes. They're very close together. So if the chord is dropped anywhere on the y-axis, I can imagine it being only dropped in some million points, discrete million points, right? And then I see the histograms, and then I can predict what sort of shape is going to correspond to the density function. Okay, so George said it should be 1 over R. And so then what's the probability the chord is what? It's what did they want to ask? The probability that the chord is smaller than the length of the length of the triangle aside. So I will get to the angle. So why is this 60 degrees here? Well, this to that. Red triangle is whatever theta. Red triangle might be, so that's a different randomization that I will describe in a moment. Okay. So first I ignore this theta. I don't see the theta. I only understand randomness as this red chord being dropped between 0 and r. Yes. And then the probability this chord is shorter than that of the triangle, the side of a triangle, is it means that I have to be above the half mark, right? Above the half mark. Make sense? Why half mark? Because, well, what's this angle here? This angle is pi over 3. And cosine of pi over 3, this side, cosine of pi over 3 is 1/2. So r has to, well, my outcome where the chord falls must be above this point all the way to this point for the chord to be shorter. So the probability of that is clearly 1/2. You see, I don't even need to do integration because I just measure the proportional length of the segment where it falls, and that will tell me the probability. Yes? You look, the guys that I can see look a little bit confused or out of it. You understand what I'm saying? There is no confusion, right? Everything's clear? Yes, everyone? Okay, so the probability then is 1/2. What is the probability then in terms of the angle theta? Now, what we can also imagine, what other ways are there to generate a random chord? I can imagine that an angle theta is selected, right? This theta here, right? And when this, that one of those angles is randomly selected, and then a chord is produced. So then the angle varies between what and what? This theta is my random variable now, right? And it's supposed to be uniformly distributed. So this theta varies from what value to what value? Yes, brilliant, right? It's from 0 to, well, not 120, careful, right? From 0 to pi, yes, right? So from 0 to pi, because look at it, when theta is 0, that means that I have a tangent right here. When theta equals to pi, you can do it in degrees or in radians, you just have different scales, it doesn't matter, you get same solution, right? I always prefer radians. So theta is between 0, it means the chord is equal to the diameter, and sorry, theta is between pi means the diameter, and 0 means tangent. Okay, so if this is randomly generated, now the density function for theta is what? If theta is uniformly distributed, the density function for theta is one over pi. Thank you, Josh, and thank you, Marcel. 1 over pi, because right, the distribution should be identically, the area of the rectangle should be equal to 1. So if it's if theta is pi units long, the height must be 1 over pi for the area to match in equal 1. Brilliant. Now, in this case, my theta, yes, please, Josh, what did you want to say? No? I saw a hand or something, whatever. So so what happens then? So what should theta be for this segment to be shorter than the side of a triangle? What should theta be? Between what and what? it should be, well, again, preferably in radians, but yes, why not? Less than that's correct, right? From so in general, so it should be from 0 tangent line, then it's very short, all the way to here where it's equal to 2 pi over 3. And of course, Ugo, you said everything correctly, right? It should be, but I just like thinking we already set it up to be in radians. So that means that what is the region of theta, relative region of theta, from 0 to 2 pi over 3? That's 2/3 of the full pi region. Yes. So that means the probability, if theta is random, the probability that I draw a chord between well, a chord shorter than the side of the triangle is now 2/3. So remember, before we said this red line is randomly distributed from 0 to r, and we found the probability to be then 1/2, so that this chord is shorter than the side of the triangle. But on the other hand, if theta is random, then we find this probability to equal to 2/3. Do you find that surprising or not surprising at all? You see, it's supposedly a paradox because I generated, you know, 2 random events, 2 uniformly distributed random events, but one interpretation gives you probability equal to 1/2. The other interpretation gives you probability equal to 2/3. Do you find that strange or not so much? Yes, strange. Well, yeah, you should think of this, right? So if the angle is random, then the distance is not proportionally random, right? So what happens here is that bigger, you know, farther distances away from 0 are basically squeezed into fewer angles, so to speak, right? Fewer range of angles. You understand? So look at it, right? From 0 to 2 pi over 3, those are the angles, the farther angles. They have more of the different angles allotted to this region, right? So, although this part is the same length as this part, they are 1/2, but what's further gets more angle distribution, right? In this case, because further means this is 2/3 of the angles are corresponding to this region, whereas only 1/3 of the angles correspond to this region. Okay, so further, no, in this case, in this particular setup, further is more likely, right? So further is more likely in this setup because 0 angle means this point, etc. Right? So further is more likely in this setup. So yes, so that's the, so if the angle is randomly distributed, it does not correspond to a random distribution of distances. Make sense? So I personally do not find it surprising anymore at all. All right, so what else is there? So let's calculate the expected value of a uniform random variable and its variance. See if you can do it just by guessing. What do you think if the random variable is uniformly distributed from A to B? What do you think is going to be the expected value without any calculations and then calculate it? What do you think it would be? Uniformly distributed from A to B, what's the expected value? You know, if you average the actual, if you simulate it and you take the average over all your simulations, what's going to be that average? That's brilliant. A plus B over 2, right? Because if it's uniformly distributed, you think about you know, about half of the values should be it's like what do you call it, nadneda or shauker, I cannot remember how to say it in English, a seesaw or something like this, right? So where it's balanced right by the center, because around the mean it's equally likely that you will get an outcome more than the mean than to get an outcome below the mean. So naturally, that should be a plus b over 2. And the calculation is very simple, right? So the expected value, just integrate from a to b, x times 1 over b minus a dx, right? Why 1 over b minus a? That's just the density function for a uniformly distributed random variable. And when you integrate this, what do you get? You get b squared minus a squared over 2, b minus a, right? Because I can factor this out, and I just have x squared over 2, plug in b, plug in a, yeah? So it's b squared minus a squared over 2 times b minus a. Well, you can set up this paradox in so many different ways, right? The way I set it, you get 1/2 and 1/3. Yeah, so then there are many versions of it. The point is that if you choose a different notion of uniformity, you have a different outcome. Okay, David? Different notion of uniformity will correspond to a different predicted probability. So we have then we have b squared minus a squared over 2b minus a. I can factor b squared minus a squared, and I do get indeed b plus a divided by 2. And now let's calculate the variance. So the variance, I need to first know what's the expected value of x squared, and that's just the integral from a to b of x squared 1 over b minus a, which ends up being b cubed minus a cubed over 3, and I have to divide it by b minus a. Now we can factor a difference of cubes. It would be b minus a multiplied by b squared plus ab plus a squared. So b minus a crosses out, and the expected value of x squared is this formula here. Good. And so now what do I do for the variance? I simply take the first number. Well, sorry, this number, and then I subtract from it the first number squared. And when you simplify it, just some algebra, you get b minus a squared over 12. So the variance is this thing. Okay? So this is just integration, so I'm hoping you don't have too much trouble with it, right? If you can figure it out. Good? So in some ways, we're going to talk about other distributions, but in some ways, the uniform random variable is the only variable there is. In other words, if you understand the uniform random variable, you understand every other continuous random variable. If you have an understanding of any other continuous random variable, you can simulate the uniform random variable. So here is how that's supposed to work. So we're going to show how to simulate the random variable, the continuous random variable x, given a uniform random variable from 0 to 1. Okay, so suppose that I have a uniform random variable from 0 to 1. I will show you how to modify it by applying a function to this uniform random variable, and I will obtain the x. I can simulate it entirely. Okay, so first of all, do you understand what I will try to accomplish, guys? Your faces are very stone, so I'm not sure, right? It seems okay. So this is so here again, the cumulative distribution is very important. I'm not really sure what's the point of it when you're dealing with discrete random variables, but I see many applications when it is continuous random variables because of the fundamental theorem of calculus. So I do not know how the density function of x is distributed. The density function does not have to be one-to-one. It can be some sort of curve that goes like mountain ridges. It can go up and down, yes? All it has to do is be above the x-axis, and I have to normalize it so that the area below it is equal to 1. That's the only requirement. But on the other hand, the cumulative distribution, right, the probability that x is less than or equal to some value a is an increasing function of a, correct? The cumulative distribution is just the probability below a particular number. And if I make the number bigger, there are going to be more numbers that contribute. So the cumulative distribution is an increasing function. It's always growing. Yes? And its range, the range of the cumulative distribution function of x. So this variable x has a cumulative distribution capital F sub x. The range of this particular function is between 0 and 1. Do you see that? Because the probabilities that you add up, it begins somewhere at 0, and it has to grow all the way to 1. So the range of this function is the numbers between 0 and 1, possibly including 0 and 1, but it's depending on the distribution. You might kind of approach, the range approaches 0 and 1, not ever touching them. So then what the first part of this theorem claims is that if I have a uniformly distributed random variable over 0, 1, I can obtain x by applying the inverse image of the cumulative distribution of the variable x to u, and that will generate x. Make sense? So that's like how do I simulate? If a computer can select random numbers, you can simulate in a computer selecting a random number between 0 and 1, you can simulate any distribution, any continuous distribution. That's what this is saying, okay? Mathematically, in other words, if I understand continuous random variables as integration over rectangles, then I mathematically understand every other distribution. Not necessarily practically, but mathematically, they are all generated as some functions of the uniform random variable. All right, so that's the first claim. The second claim is that if I'm given any continuous random variable, I can use it to simulate a uniform random variable. Okay, so if I have a phenomena where I'm able to simulate a continuous random variable x, I can use it to create a simulation of a uniform random variable. Okay, so as long as I have one continuous random variable, I can get to every other. Right, so they are in some sense isomorphic to other variables. They're all very much the same, logically the same. So again, here is the proof of part 1. So observe that again, that the cumulative distribution for the random variable x is taking real numbers and it's mapping them into 0, 1, correct? Because it's just calculating probabilities into 0, 1, and that has to be an increasing function. Yes? So if I have a uniform random variable over 0, 1, then I can set up y to equal the inverse image. This is just a function, right? It's just really, when I think of it as a function, there is nothing that happens here by chance. It just maps different real valued numbers. So it maps different numbers in R to numbers between 0 and 1. So it's just a concrete real valued function. And it has an inverse because it's an increasing function, yes? So if I take the inverse function has 0, 1 as its domain, and its range is some subset of real numbers, right? It just goes in the other direction. Actually, not some subset, you might say it's all real numbers, right? Because this function can take any real number and transform it in between 0, 1. So if I start with the inverse, it takes numbers between 0 and 1 and maps them in one-to-one fashion onto R. So I can set y equal to f inverse of u. Yes, and then I can calculate the distribution of y. What's the distribution of y? Well, it's the probability that a is less than or equal. So y is less than or equal to a. Y has to be less than or equal to a. That's the cumulative distribution for the random variable y. Yes? And I want to calculate the density function. I want to know what's the density function of y. And that would be the derivative of the cumulative distribution of y, which is the derivative of this probability. But this probability is equivalent, right? The probability that this random variable is less than or equal to a is the same as the probability that u is less than f of a, right? So this point is the same as u less than the cumulative distribution of x at a. And that will be the integral from 0 to this value, right, of the variable u. It's just, you see the density here is 1, which if I integrate, it just amounts to the cumulative distribution of x. And when I take the derivative, I have the density function of x. You see, so this y at any point a, this y at any point a has the same density function, which means that that mathematically they are the same, right? Y and x have the same probability density function, so they are identically distributed. So did this proof make sense, guys? Makes sense, right? I mean, I'm not sure. It feels to me today that somehow the way I say it is not good. But I'm hoping, maybe it's because I look at your faces and your faces look not very impressed, right? So, but I'm hoping that's very clear. It's something that you might have even figured on your own, why to make such a distribution, right? It's just you translate x into a uniform distribution here. On the other hand, you can just, of course, it's an inverse operation. On the other hand, you can define, if you're able to generate the random variable x with its probability density function and its distribution, you will be able to simulate uniform distribution. And how you do that? Well, if you just take x and apply to it its cumulative distribution function. Okay, so you create this variable and you label it as u. So this variable clearly is it's ranging between 0 and 1, because the function will produce results between 0 and 1. Yes. So u is already correctly bound between 0 and 1. And then what's the probability that u is less than or equal to a? Well, that's the cumulative distribution of u. And I can obtain the density function for u by taking the derivative of the cumulative distribution. And that amounts to taking the derivative of the probability that the function at x is less than or equal to a, which is the same as taking the derivative of x being less than or equal to the inverse at a. They are increasing, so I can just apply inverse here, and I obtain this probability. And what is this derivative? Well, first of all, this here, px less than or equal to f inverse of a, that's just the cumulative distribution of x evaluated at the inverse map here. So it's fx of f inverse here, and they cancel each other out. Yes. So really, I'm just taking the derivative of a, which is 1. So you can see that u has density function equal to 1, which means that it's a uniform random variable. Yeah? Make sense? Good. So again, what is this function doing? This function, if you try to think of it intuitively, this function is just reshuffling, right? So you can, here is how I try to imagine it, right? So what I imagine is I have a uniform random variable, right? And it's drawn on a rubber band, okay? And I can generate other functions by stretching or compressing the rubber band in different locations, right? So it's really the same distribution, but you see the rectangle has to, see here used to be, the rectangle used to have the same height, but if I squeeze it, the rectangle has to go up, right? If I squeeze a segment of the uniform distribution, the rectangle has to go up. If I stretch it, it might have to prolapse. And so I can play around with this rubber band, and I can just change it in different locations and shape the density function accordingly. Yeah. So that's why, to me, at least, it's intuitive that using the uniform random variable, I can generate I can generate the other random variable that is continuous. Okay. So let's start with the normal distribution. That's the next part. All right, so normal distributions. So first, let's define the standard normal distribution. So Z, you might know it as a Z-score, is said to have a standard normal distribution if it has a probability density function phi given by this formula. Now, you might not right away figure out why such formula is, why would you think of such a formula? That's later, right? Right now, just let's take it as a given. This is our density function. So what we first want to verify is that it works as a density function over numbers between minus infinity and infinity. In other words, that the area below this curve equals to 1. And for that, we just need to verify that the integral from minus infinity to infinity of e to the minus z squared over 2 is root of 2 pi. And we can do this as follows. So I'm going to label this integral as I. That's going to be the number. And I can clearly change z to any other letter. So I'm going to change z to x and to y. Okay? Those integrals are exactly the same. Okay, so then if I multiply I by itself, I get I squared. So I can multiply the version of the integral involving x by the version of it involving y. And when I multiply those quantities, you would realize, I hope, that I obtain the integral from minus infinity to infinity of the product of those functions, right? So it's e to the minus x squared plus y squared over 2. Yes, that's just from integration theory from Calc 3, right? So it's very convenient if I can break into two pieces, one piece depending on y, another depending on x. I can always bring them together or bring them apart. You might kind of play, or just thinking about it, you hopefully realize why this is true. And of course, in this form, it's still not convenient to integrate, right? It's not easy to find the antiderivative of this expression. It's impossible to do so, in fact, using your simple functions, sine, cosine, exponentials, things that you learned from calculus. So what you do is you try to describe the same integral using polar coordinates. You say, why do you think of polar coordinates? You have x squared plus y squared. If you replace that by r squared, you have your polar coordinates. So the region, as I call it, frying pan, right? The region is O of r. So O of r is like an infinite rectangle. But I can also imagine it to be an infinite circle. In other words, a circle or a disk of infinite radius. So if it's to encompass O of r2, the angle here, theta, goes from 0 to 2 pi. And the radius, to make it an infinite circle, goes from 0 to infinity. Then I replace x squared plus y squared by r squared, because root of x squared plus y squared is r. So this is minus r squared over 2. And then I have to not forget that if it's polar coordinates, again, guys, I'm hoping that you remember integration and that you don't need a review for it. And if you remember integration, you know that when you change to polar coordinates, you have to multiply by the corrective factor r. Okay, so I have r dr d theta. Okay, so that comes out as a result of changing variables. So what is this integral? First of all, I notice that this part does not depend on theta, so I'm able to factor it into two parts. Makes it simpler. I'm factoring it into an integral from 0 to 2 pi of d theta, and that identically equals to 2 pi. And this single variable integral, which is not at all hard to solve. This can be solved by u substitution. You can see that the derivative of r squared over 2 will be r, right? So it's like the integral of e to the minus u. if you think of it kind of quickly, this is the integral of e to the minus u, which will be minus e to the minus u, evaluated from 0 to infinity. Okay, here I just kind of, you don't have to do u substitution. If you're kind of, if you had to do calculus for a long time, then you just kind of do it in your head. So it's e to the minus r squared over 2 with a minus, and then you plug in 0 and infinity. At infinity, this is identically 0. At 0, it's 1, right? So you're left with 2 pi multiplied by 1. And so that is the result for I squared. What is I? Is the square root of this number. So that's where I get the root of 2 pi. Yes? So the cumulative distribution is then written as the integral from minus infinity to z of phi of dt, which is this integral. And you would observe that, you know, this distribution has many nice properties regarding symmetry. So the nice properties are as follows. So the density function is even. So if you replace z by minus z, the function is not changed. Yes, that's because of this z squared factor. The minus is not affecting it. And then we have symmetry of tail areas. In other words, the cumulative distribution at minus z is always equal to 1 minus the cumulative distribution at z. And you might observe it, you know, because think about it. What if z is a positive number, and let's say minus z is to the left of 0, then this quantity is the probability that z is less than or equal to minus z. And because the density function is symmetric, the density curve is like bell-shaped curve, it's symmetric, the probability you're below minus z is the same as the probability that you're above z. Yes? Which is 1 minus the probability that you are below z. You can always replace less than or equal to by strictly less than, because the probability z equals z is 0, right? It never equals a particular number. So we have 1 minus probability that z is less than z, which is this thing, okay? And you can of course observe that formally. Here I assumed that z is positive and minus z is negative, but this assumption is not necessary. So formally, the cumulative distribution at minus z is the integral from minus infinity to minus z of this thing, of the density function. And I just carry a very simple u substitution. I let u equal to minus t. And then what do I get? I get here, this is just t, so I get minus u squared. And then what is this number here? This is t equal to minus z, which means u equals to z. This is t equal to minus infinity, which means u equals to infinity. So I have integral from infinity to z of this expression. And dt equals to minus du, right? Du equals to minus dt, so dt equals to minus du. I take this part, it's equal to that part. And then I take this minus, I put it in front, and you know that when you have a minus in front of an integral, it disappears once you invert the integration sign. So you take this, if you replace it to be the integral from z to infinity, there is an extra minus coming out, and then the minuses cancel each other out, and I get this. And that's just an integral from z to infinity, which is 1 minus the integral from minus infinity to z. See? So I verified this property using calculus. Another thing is that if I take, this is also pretty obvious, if I take z and I multiply it by minus 1, so here is z, you imagine the bell curve multiplied by minus 1, you flip it over, right? And they will be identically distributed. It's also a standard, you know, they're not identical random variables, certainly, but their distribution is identical, right? So so z and minus z are both standard normal distributions. And we can simply see that as follows. So the probability that minus capital Z is less than or equal to Z is the same as the probability that capital Z is bigger than or equal to minus Z. Right? I just multiply by minus 1 and change signs. So it's the probability that Z is bigger than minus Z. And that is the same thing as well, as 1 minus this cumulative distribution at minus z, right? Because right, if I evaluate the distribution for z, this is bigger than some number. It's always 1 minus every probability that adds up to minus z, which, using part 2 of this formula, I can replace this part by 1 minus phi of z. So this I can replace by 1 minus phi of z, and you have 1 minus minus. The ones cancel out, and we are just left with this. Yeah. So they have the same cumulative distributions and therefore identical density functions. Now let's calculate the expected value and variance of a standard normal distribution. What do you think? Could you please try calculate the expected value of a standard normal distribution? I'm sure you can imagine what it is even without any calculation. So guys, you see, I asked you if you could. Please calculate, yes, alive, beautiful, it's 0. Was there any calculation necessary? First of all, you all have seen the bell-shaped curve, right? Here, the bell-shaped curve is centered around 0. But let's say right now you are not seeing this right away. You just see this density function. The expected value of z is the integral from minus infinity to infinity of the density function multiplied by z. And this here is an odd function, so I don't even need to bother integrating. I could if I want to, but it's an odd function at a balanced interval. So you have plus area minus area. They cancel each other out, and you get 0. Yeah. So the expected value of z is indeed 0. Now we need to calculate the expected value of z squared. So the expected value of z squared, it's the same integral, but I have here a z squared. And now the function is even. And integrating an even function is the same as integrating it from 0 to infinity and doubling it, right, of z squared e to the minus z squared over 2. Yes? And this integral can be solved by, so this integral may be solved by, what do you call it? Integration by parts. So integration by parts, I'm going to take out z here, and then integrate z times e to the minus z squared, and I obtain this part, which is identically reduced to 0 once I put in the bounds of integration, and then plus the integral where now I integrate z times e to the minus z squared over 2 and differentiate the extra z that I have, and I get this integral. Right? You all remember integration by parts, guys, right? I don't need to explain this. So and then this integral, it's a difficult integral, but I already know something about it. It's from 0 to infinity, and this is half. This is half of root 2 pi, right? Because if it were from minus infinity to infinity, it's an even function. That would be root 2 pi, as we calculated above. And now we just have half of it. So we end up with the number 2 over root 2 pi multiplied by root 2 pi over 2. They cancel each other to 1. That means that the expected value of z squared is equal to 1. And variance of z is then very simple to calculate, because variance of z is the expected value of z squared minus the expected value of z squared. Now this number is 0, so variance is equal to 1, because it's just equal to the expected value of z squared. Okay, good. So having worked with a standard normal distribution, let's define the normal distribution as follows. So we would say that x has the normal distribution if it's of the form mu plus sigma times z. Yes, it's mu times sigma, mu plus sigma times z. So would you do me this favor? Please calculate the expected value of x and the variance of x based on your knowledge of the corresponding data for z. You know that variance for z equals to 1 and expected value for z equals to 0. So tell me what's the expected value of x and what's the variance of x. Guys, you all went to sleep, it seems. I only see one person. So sigma is standard deviation, yes. Just a root of variance. Oh, good. Boker Tov. All right. So the expected value clearly is, expected value is linear. So it's mu plus sigma expected value of z, which is mu, as Eli just said to me. Thank you so much. Can you now calculate the variance? No, it's not mu plus 1. Careful. Variance, well, see if you can correct it. Variance should not be affected by a shift. So mu is like a shift here. When you what do you do? When you calculate variance, in essence, you take x minus its average, and then you square it, and then you take the expected value of that. So since mu was the average, it should disappear when you take minus. So the answer is very close to what you said. What's the answer? So the answer is sigma squared, you mean? Yes, that's brilliant. Sigma squared. Okay. So here is the calculation, right? For the expected value, again, it's linear. So the expected value of a constant is the constant. Then plus expected value of sigma z. I can factor the sigma, and I just get mu because this is 0. For the variance, I would calculate x minus the average. Once I know the average now, I calculate the expected value of x minus the average squared. And that reduces to, I subtract mu from it, so it's just the expected value of sigma z squared. So that's just the expected value of sigma squared z squared. And now I'm able to factor out the sigma squared, yes? So it's the expected value of z squared times sigma squared. And we know that the expected value of z squared is 1. And we can go, usually what we do is if you took some classes in psychology or in statistics, right? So usually you're given this variable x, and you convert it to the standard normal distribution, to the z-score, right? Why do you convert it to z-score? Mostly because, especially before, you did not have powerful machines to kind of recalculate, or the setup in general, right? The machine understands only the normal distribution when it's in standard form. What do? You're just renormalized to make it into a standard form. You translate your data into a standard form, which you accomplish as follows, right? If x is mu plus sigma z, then z is x minus mu over sigma. Okay, make sense? And then we can verify what is the cumulative distribution for a random variable x that is normally distributed. So the cumulative distribution is the probability that x is less than or equal to little x, which is the probability mu plus sigma z is less than or equal to x, which is the probability that z is less than or equal to x minus mu over sigma, which is then how do you say this letter in Greek anyhow, right? To me, it's fe, but that's because it's in Russian, right? So this letter is phi or fe of x minus mu over sigma. Okay, so then the density function can be obtained by differentiating. So I take this function, this cumulative distribution, differentiate, and when I differentiate this function, I get little phi x minus mu over sigma times the derivative of what's inside, which is 1 over sigma. Yeah, which what is this? This number I have to square and divide by 2, so that's what I get. And then the 1 over sigma I can carry over here, and that is your normal distribution, right? I'm hoping that because we started with the standard normal, you can more quickly figure out what's the density function for the normal distribution. And you might be familiar with the following rule: the 68, 95, 99.7% rule. And that tells you that if x is normally distributed with mean mu and variance sigma squared, then the probability that x falls within 1 standard deviation away from the average is 68%. The probability it will fall within 2 standard deviations is 95%, and the probability it falls within 3 standard deviations is more than 99%, 99.7%. Okay, so it's very likely that x falls within 3 standard deviations. And here is an exercise. Let's see if we can solve it. So let x be normal with mean -1 and variance 4. I want you to tell me exactly in terms of the cumulative distribution for standard normal, what's the probability that absolute value of x is less than 3, and then use those rules, if you can, right? Use this rule to approximate what this probability is. Good? I'm not sure if he is around. If you're thinking of it, you know, my brother was asking this. I mean, have you watched Babylon Berlin? Anyone of you on Netflix? It's a random question. I'm just saying that you're sleeping, and I'm thinking, well, are you watching? You are watching Babylon Berlin, which the first two the first two seasons. How many episodes have you seen then? Oh, here you go. Some people wake up. Right? We talk about Netflix on season 1. Maybe that's why you're not disappointed by it. It began very interestingly. You know, it's like the Weimar Republic in the 1920s or 1930s. So it was interesting to me because of it. But then, my God, they really botched it, and now they produced another season. I have watched the first 2 seasons, right? And then right now I know they released a new one, which surprised me because I figured they got really lazy at the end. It's like it begins to make less and less sense and become stupid, unfortunately. Well, I think it's easier to get that vision living today. It's very obvious how things happen. Have you seen? You know, you had this official, what do you call it, Corona rat line, and then some people were trolling it. They were saying, "You are doing the right thing by calling us." You know, people are calling, and I've seen a bunch of people that I know. Right? Oh, you know, some people are congregating. Let's call on them. You are doing the right thing. In Israel, by the way, they have made quite a show for that. It's pretty funny. Do you know who goes to my cemetery? The mayor of New York. He actually goes there. My brother filmed him. It's that popular. Why does he go there? You know, because it's a nice park. You understand? It's what you call it. It's a loophole. People are afraid to go to a cemetery because, well, people are, you know, there are gravestones there. But that means that you have, unlike in Prospect Park, you have a very huge, nice, wonderful, empty place to hang around and do whatever you like. All right, guys, I hope I'm not distracting you too much. You are able to calculate this probability, yes? If you have to go, you can, of course, go. I will finish this problem before I disconnect. Oh, too bad, too bad. All right, well, nice seeing you. I hope you are doing well there, not getting sick, not getting bored. Yes, see you. Talk to you later, though. I'm not sure what is TY first and what's GN last. That's thank you. Interesting. And then what's GN? Good night. You see? Good. Oh, ja. Ja, das sagten wir auf Wiedersehen.
So could we go over the problem?
Well, I thought you were resting already, but...
No, I'm just waiting.
All right, let's go over the problem. So the probability that x is less than or equal to 3 I have no idea what that means, but I'll try to figure it. Okay, so absolute value of x less than 3, it means x is between -3 and 3. And I want to convert it to z-score. So I need to subtract from each value the average, which happened to be -1. It was given to me as -1. And then I have to divide by the standard deviation, which is 2. All right, guys, goodbye if you're leaving. I hope to see you on Wednesday. So you divide by 2. Now the middle becomes z, and then we have -1 on the left and 2 on the right. And this now is what? This is just integration. What is the cumulative distribution? Nothing more than the antiderivative, right? So remember, like in Calc 1, you evaluate at 2 and you evaluate at -1, okay? This is the exact solution if you could calculate it, okay? This is an antiderivative, plug at 2, minus the antiderivative, plug in -1. Now, I will show later, I suppose, in the next class, is that you can use an integration table if you don't have a computer. It's already becoming obsolete, right? So how do you estimate those numbers? Well, usually those tables are not containing negative numbers to save space, so you need to convert for the number to be positive. So what you do is you write it as 1 minus phi of 1, and then when you simplify, it's basically phi of 1 plus phi of 2 minus 1. Yeah. And if you want to approximate it, the approximation, and let's say we only have this information available to approximate. We don't have a computer to integrate. So to approximate it, we are going to use this fact. So the probability that that x is between -1, that z, sorry, is between -1 and 2 is the same as the probability that z is between -1 and 1. And this gives me 68%. Or 0.68, and plus the extra probability that z is between 1 and 2. And this I will try to approximate as follows. What is this number? This is like the probability that z is between -2 and 2, minus the probability that z is between -1 and 1, and then I get the two tails, correct? You see what I'm saying, right? I have this distribution between -2 and 2, and within it I have -1 and 1. I cut it out, and I have now the distribution between -2 and -1 and between 1 and 2. And they are symmetric, so I then divide it by 2. So I take this minus that, divide by 2, and I have an estimate for this guy. So the first is 0.68, and the second part, this is 0.95 minus 0.68 divided by 2, and my estimate is 0.8, what is it, 815, right? Good. So that will be enough, I suppose, for today. Do you have any questions from me? I suppose I'll stop recording.